Hello everyone, I'm Alejandro Gallego, and today I'm going to present to you our research methods called anomaly detection using density matrices and kernel density estimation. I work with Oscar Bustos and Fabio González, and we come from the National University of Colombia. Let me first introduce the background of our research method. Our method is framed in the union of statistics, machine learning, and anomaly detection. We use the method kernel density estimation and novel neural density estimation to prove our novel method. Anomaly detection is one of the principal tasks in machine learning systems. First, anomaly is an observation that deviates considerably from one concept of normality. Also is known as novelty detection or outlier detection. It can be solved using supervised, unsupervised, or semi-supervised approaches. There are multiple applications like medical anomaly detection or fraud detection. And the anomalies can be a point anomaly or can be a group anomaly, and also there are more high-level semantic anomalies. When the ratio of the anomalies are really high, we can use a supervised learning approach and classify every anomaly. However, the ratio is typically low, so we need another approaches like density estimation. There exist different kinds of models to anomaly detection. Some of them are based on classification, probability, reconstruction, or distance. It can be more traditional ones like shallow methods like KNN or iForest, and another more deeper ones as autoencoders or variational autoencoders or one-class neural network methods. We base our model in density estimation. A probability density function defines the likelihood of a given random variable. We want to estimate that probability density function using the data set. There are two principal approaches. One of them is the parametric approach, and the other one is the non-parametric approach as kernel density estimation. Kernel density estimation is a non-parametric density estimation method where there is no any particular assumption about the underlying probability density function. The kernel density estimation is an unbiased estimator of the probability density function, and commonly we use the Gaussian kernel, as you can see at the bottom right of this slide. However, kernel density estimation has several problems. The first one is that it's an inefficient algorithm because it needs to store every training data point in the training phase. Besides, it is not designed to deal with high-dimensional data. And moreover, it is not designed to be differentiable, so it can be combined with deep learning methods. Because of that, its efficiency is linear in terms of the training data points. Thus, our problem statement is that we want to create a novel method that is not a memory-based algorithm. Also, it is differentiable, so we can integrate with novel deep learning approaches, and we can use to solve anomaly detection problems. Taking into account these problems, we propose density matrices kernel density estimation. That is an efficient approximation of kernel density estimation. Also, is non-memory based, solving the problems with efficiency. Also, it's a differentiable algorithm, so we can combine with other deep learning approaches. We have two main ways of training. One is an optimization free, and the other one is a stochastic gradient descent approach. Our method is based on two main ideas. One is the proposed by Rahimi et al. In 2007 that calls random Fourier feature to approximate the Gaussian kernel. And the second idea is the density matrices that is used in quantum mechanics. Kernel methods are usually used in machine learning tasks. It's a classical one where we want to induce a future space given by a kernel function. The kernel function can create an embedded space that is high or can be an infinite dimensional space. The problem with kernel methods is their efficiency. Rahimi et al. Proposed random Fourier feature that approximate the feature space of a given kernel using linear methods for calculating nonlinear kernels. We also provide a further optimization using neural networks called adaptive Fourier features. Density matrices is a formalism in quantum mechanics that provides the probability of a given quantum system using the Born rule. It's a more general model of probability, and it can combine linear algebra and probability. Calculating a categorical distribution using the density matrices is obvious, but is not efficient. So a problem is how to create arbitrary distributions for a mixture of non-parametric probability distributions. Therefore, our method is anomaly detection using density matrices and kernel density estimation. It had 3 stages. The first stage is the training stage, where we generate normal data points for the random Fourier feature. We optimize those parameters with adaptive Fourier feature. The third step is embed each training data points in the embedded space of the random Fourier feature. And we also normalize each embedding step. And the last step in the training stage is to calculate the density matrices as the outer product of the training embeddings. The validation stage, and also called the hyperparameter tuning, the first part is to embed every validation sample in the random Fourier feature. Second is to calculate the density of each validation sample using the Born rule. The third one is calculate the threshold theta as the discriminator using the validation samples. The last stage of the algorithm is the prediction stage, where each test sample is embedded using the random Fourier feature. We calculate the density using the Born rule, and using the threshold, we classify normal and abnormal data points. For testing, we provide an experimental setup using 20 data sets. Our results shows that our model is on a par or outperforms state-of-the-art algorithms, as you can see in the graph. The conclusions of the algorithm is that our novel methods show better performance than state-of-the-art algorithms. Also, it is not affected by the anomaly rate. In contrast with other methods as the kernel density estimation, it doesn't have huge memory requirements. And as a future work, we will combine our model with deeper ones as autoencoders and variational autoencoders. Thank you.